Bismillah ar-Rahman ar-Rahim. First of all, I would like to thank the organizing committee of the conference. Uh, Today, I want to introduce algebraic hyperstructures and fuzzy algebraic hyperstructures. Uh, First, we begin with ordinary sets and characteristic functions. I don't explain about ordinary sets چون I know all of you know ordinary sets. And also everybody of you know about the operation on sets like union, intersection, complement, and subset. Here we have the definition of characteristic functions. If we consider X as a universal set and R be a subset of X, we can define the characteristic functions of A from X to the set of 0 and 1 by the definition that you see. It is equal to 1 if X belongs to A, and it is belong to 0 if X is not in A. The following theorem help us to better understand the notion of fuzzy sets as a generalization of ordinary sets. Here, the first theorem say that A is equal to B if their characteristic functions is equal. And the second theory, let X be a universal sets, A and B subsets of X, then characteristic function of the intersection is equal to the minimum of characteristic functions. The characteristic functions of union is equal to the maximum of characteristic functions, and the characteristic functions of complement of A is equal to 1 minus the characteristic functions in X. What are fuzzy sets? The processes that are modeled in the real world are usually not exact. Usually, the reality associated with uncertainty cannot be modeled as it is, and we have limitation in modeling. Fuzzy sets enable one to work in uncertain and ambiguous situations and solve ill-posed problem or problems with incomplete information. Fuzzy sets are sets whose elements have degree of membership. Fuzzy sets have been introduced by Professor Zadeh as an extension of the classical notion of sets. Here we have the definition of fuzzy subsets of a universal set. Let X be a set. A fuzzy subset A of X is characterized by a membership function mu from X to unit interval 0, 1, which associate with each point X in X its degree uh, of membership function. For example, we can define a possible membership function for the fuzzy subsets of real numbers close to 0 as follows. Mu x equal to 1 over 1 plus 10 x2. Using this function, we can determine the grade of each real number in this fuzzy subset, which signifies the degree to which that number is close to 0. Also, it is possible we define the membership functions as indicated in this example. We can define the operation of fuzzy subsets similar to characteristic functions of ordinary sets. Here you see, for example, uh, the definition of union, intersection, and complement of a fuzzy subset. Also, we can define inverse image and image of a fuzzy set. Let F be a mapping from a set X to a set Y, and mu be a fuzzy subset of X, lambda be a fuzzy subset of Y. Then the inverse image of F is the fuzzy subset of X defined by F inverse lambda in X equal to lambda F of X for all X in X. The image F mu of mu is the fuzzy subset of Y defined the last formula for all Y in Y. Also, we can define some elementary of properties of ordinary sets to uh, fuzzy subsets that you see in this page. Notice that when the range of membership functions is restricted to the set uh, of 0 and 1, these functions perform precisely as the corresponding operations for crisp subsets. For the sake of simplicity, we will represent every fuzzy subset by the membership function. For any fuzzy subset mu of X and any t belong to unit interval 0 and 1, we define two sets as upper t-level cut and lower t-level cut of mu. The first one is upper and the second is lower T-level cat. I suppose that you know the definition of group, the definition of ring, and also the definition of module. Now we want to define the definition of fuzzy subgroups of a group. This notion, for the first time, defined by Rosenfeld. The definition is let G be a group, a fuzzy subset mu of G is called a fuzzy subgroup if one, the minimum of mu x and mu y less or equal than mu xy for all x and y in G. And the second condition, mu of x less or equal than mu x inverse for all x in G. The following elementary facts about fuzzy subgroups follow easily from the axioms. 1. Mu of x is equal to mu of x inverse, and mu of x is less or equal to mu of e, where e is the unit of G. Also, mu, if satisfies the condition 1 and 2 of our definition, is equal to the last condition you see in this slide, the minimum of mu x and mu y less or equal than mu x y inverse. The second structure that we have in algebra is the notion of ring. Leo introduced and studied the notion of fuzzy subrings and fuzzy ideals of a ring. The definition is as follows. If R is a ring and mu is a fuzzy subset of R, then mu is called a left, respectively right, fuzzy ideal if it satisfies the following conditions. 1. The minimum of mu of x and mu of y less or equal than mu of x minus y for all x and y in R. This condition is similar to the condition for fuzzy subgroups. The second condition, mu of y, less or equal than mu x dot y, respectively, mu of x less or equal than mu x point y. The subset mu of R is called a fuzzy ideal if it is a left and right fuzzy ideal. Another structure is a module. The concept of module was introduced by Neguita and Ralesco. Definition. Let M be a module of a ring R. A fuzzy subset mu in M is called a fuzzy submodule of M if for every x and y in M and R in R, the following conditions are satisfied. First, mu of 0 equal to 1, of course, we can remove the first condition of this definition. It is not necessary, but for the first time, Neguita and Rolesko considered this definition in uh, their definition. The second, the minimum of mu x and mu of y less or equal than mu x minus y for all x and y in M. And the last condition, mu x less or equal than mu rx for all x in M and R in R. Now I want to introduce algebraic hyperstructures. The concept of hyperstructures was introduced by Marty at the 8th Congress of Scandinavian Mathematicians. Hyperstructures have many applications to several branches about pure and applied sciences. The first definition, let H be a non-empty set and start from H cross H to power set of H minus empty set be a hyper operation. So any function from H cross H to power set of H minus empty set is called a hyper operation. And the couple H and star is called a hypergroupoid. In this picture, you see what is the meaning of the definition. In the definition of hyperstructure, for example, if our hyperstructures be circ, then the combination of two elements of H is a subset of H, not a singleton. One of the example of hyperstructures is billet group. Billet groups, you are familiar to billet groups. In this table, you see, for example, if the bullet groups of parents of a child, for example, one of them be A and another one be again A, then the possibility for billet groups of their child is O or A. Another definition is the definition of hypergroup. The definition of hypergroup is a generalization of group that all of you know about group. Here we have the definition of generalization of group. A hypergroupoid H is called a hypergroup if we have associative law, and the second condition, A star H equal to H star A equal to H for all A in H. This condition is called the reproduction axiom. The second condition is frequently used in the form, given A and B in H, there exists X and Y in H such that B belong to A star X and B belong to Y star A. Note that in the first condition, when we say A star bracket B star C bracket equal to bracket A star B bracket star C. This is the equality between two sets, so different to ordinary associative law. Here I want to introduce some books about algebraic hyperstructures. One of them is the book of Corsini. You see, hypergroup, hypergroup theory. Another one, a joint book of Corsini and Leoriano Fota. Also, here you see uh, other books about algebraic hyperstructures that I wrote these books with Professor Wooduklis and Professor Leoriano Fota. One of them is about hypergroup. Two books are about hyperring. Also, hyperrings are generalization of rings. Here you see the definition of hyperring. The following definition introduces a hyperring in general form. Both addition and multiplication are hyperoperation. A hypergroupoid H is called a hyperring if the following conditions are satisfied. You see, the first, we must to have a commutative hypergroup with plus and a semi-hypergroup with dot. A semi-hypergroup is algebraic hyperstructure that have a algebraic hyperstructure that has only associativity. And the last condition is distributivity for elements. Here you see the definition of hyperideal of a hyperring. Again, this definition is a generalization of ideals in a ring. And also in this slide, you see the definition of hypermodule as a generalization of ordinary module over a hyperring. We can define sub-hypermodule of a module. You see here the definition. Let M be a hypermodule of a hyperring R. A non-empty subset S of M is called a sub-hypermodule of M if the following axioms holds. 1. S together with plus is a sub-hypergroup of M. R point S is a subset of S. Also, we can define the definition of homomorphism between two hypermodules. You see the conditions. The conditions are similar to the homomorphism of modules, but we notice that the equality in the condition is that the equality of sets, not elements. Now we want to introduce fuzzy definition of subhypergroup. Let H be a hypergroup and mu be a fuzzy subset of H. Then mu is said to be a fuzzy subhypergroup of H if the following axiom holds. I don't read the axioms. You see them in the slide. Indeed, these conditions are generalization of condition of subhypergroup. This definition is belong to me for the first time when I was a PhD student. I introduced this definition for fuzzy subhypergroups. In this definition, we have the definition of a fuzzy hyperideal of a hyperring. So the condition 1, 2, and 3 must give us the definition of fuzzy subhypergroup, and we have also another condition, the fourth condition, mu of y must be less or equal than the infimum of mu of z when z belongs to x point y, and mu of x less or equal to infimum of mu z when z belongs to y point x. Sorry, the last line is z belong to y point x. And finally here we have the definition of fuzzy subhypermodule of a module. One of the generalization of the notion of fuzzy sets is intuitionistic fuzzy sets. Intuitionistic fuzzy sets are introduced by Atanasoff. As you see, if we consider A equal to the subset, the set of X, mu of X, and lambda of X when X belongs to X, where mu and lambda are membership functions that from x to 0 interval set 0 and 1. But here we say mu is membership function, lambda that is also from x to interval, unit interval, is non-membership function. And the addition of membership function and non-membership function must be between 0 and 1. We can define operation on intuitionistic fuzzy sets similar to fuzzy sets, but in the definition, for every operation, we have membership function and non-membership function. For example, if you consider the intersection A intersection B, the membership function of A intersection B is the minimum of mu x and mu x. All of these two membership function of A and B respectively, and the non-membership function is the maximum of lambda A and lambda B in X. So the first definition of fuzzy algebra was fuzzy subgroup. So here we see the definition of intuitionistic fuzzy subgroup. Let G be a group and A be an intuitionistic fuzzy sets in G. Then A is called an intuitionistic fuzzy subgroup in G if the following conditions holds. Here you see the condition. Two of them is for membership function, the condition 1 and 2, and two conditions are about non-membership function that you see, condition 3 and 4. The next definition, let R be an ordinary ring. An intuitionistic fuzzy set A in R is called a left, respectively right, intuitionistic fuzzy ideal of R if we have the following conditions. If you consider the condition 1 and 2, condition 1 and 2 are related to membership function, and condition 3 and 4 are related to non-membership function. The next definition, you see the definition of intuitionistic fuzzy submodule of a module. This definition is also similar to the definition of ideals or subgroups in fuzzy case. Now here we have the definition of intuitionistic fuzzy subhypergroups of hypergroups. An intuitionistic fuzzy set A in H is called an intuitionistic fuzzy subhypergroup of H if we have the following four conditions that you see. Here you see some lemma and theorem about intuitionistic fuzzy sets. There exist many results about this definition, but today only I decided to introduce the definitions. Here again some elementary results about intuitionistic fuzzy sets. And if you be interested to find the algebraic hyperstructures, you can see here a book about this concept. Finally, I want to introduce some papers, some application papers about these concepts. First, an application of intuitionistic fuzzy sets in medicine. You see the name of journal. Another one is this paper, twin hypercube for intuitionistic fuzzy sets and their application in medicine. Another one, a new relationship between population genetics and fuzzy sets. And also a new relationship between intuitionistic fuzzy sets and genetic. And this is another paper in FACTA universities. But finally, the last paper you see on quasi-ordering hypergroups, ordered hyperstructures, and their applications in genetics. Thank you very much for your attention. Goodbye.